So now in this video we're going to look at using the 555 timer in monostable or one-shot mode. So right now we're in the stable position. The output is actually low. We could add another LED and look at that if we really want to. So I'll put that to the positive rail, and the green LED is lit up if we want to do that. Once we hit the button, then the output went high. So we forced it out of the stable state, but once the timing was done based on that capacitor and resistor, it went back to its normal state. Now we can use 10 times the resistance. That was a 1 kilo ohm resistor. We'll look at this later. So this resistor is going to the positive rail. I realize the capacitor is hiding that. There we go, the positive rail, and there's a little jumper there. We'll get to that later. But now we have 10 times the resistance for a given capacitor, and so it's going to take 10 times longer. Instead of about a second, it's going to be about 10 seconds. Actually, probably about 11 seconds versus about 1.1 second. Normally, though, when you see this, you will not see that second LED. You'll just see the 1 LED, and you'll power something for a brief period of time, and then you want it to shut off based on when you trigger it. So now here's a schematic I drew, and I drew it up to fit how it's going to work with the physical component pretty well. I'm not going to use the 10 nanofarad capacitor to pin number 5, but that may help address stability issues, as does this 10 microfarad, which is 1,000 times, or no, 1,000,000 times larger than 10 nanofarads. This 10 microfarad capacitor is helping to smooth out problems with the power supply not providing a stable enough voltage for this integrated circuit. Now, I do have a little jumper right here. We'll look at that since that's the hardest to see right now. So you can see between pin 7 and pin 6, we have just a direct connection right there. And that's because we're going to charge the capacitor through a resistor, and then it discharges through pin 7. So pin 6 is the threshold pin. We looked at that in the last video, which was a bonus video, not part of the series. But in any case, it looks for a 2/3 power supply voltage, whereas pin number 2 waits for 1/3 or less of the power supply voltage. And so we're going to take a, doesn't matter what value resistor we use really, other than timing. So for a 1,000 microfarad capacitor, as we said, if we want 1 second, which is nice for videos because 10 seconds is kind of a long time, we will take a 1,000 microfarad capacitor and put it to pin 7. We could put it directly to pin 6 too. Doesn't matter. That's one node. It's a direct connection. Now we're going to take a 1,000 microfarad capacitor. This can only operate up to 35 volts, but the 555 timer is probably closer to 15. This one may be 18 or something, but this is an NE555. Make sure you don't exceed the voltage of your 555 timers, but since 5 volts is common, I must put that in backwards, so the positive side to pin 6. Since 5 volts is common, I'm going to, for the most part, be using 5 volts in my videos, right there. Now for the switch over here. It's one we've been using recently, so I'm not going to go over it too much. When I'm not pushing the switch, I want this 10 kilo ohm resistor to the positive rail, whether I'm pushing the switch or not actually. I want it to the part of the switch that connects to pin number 2, the pin node there, because it's waiting for a low voltage, and the negative rail will do it. It doesn't take in or let out any current other than some leakage or whatnot. It just looks at the voltage. So we can use 10 kilo ohm, we close the switch, all the current that goes through the resistor will go to ground. Pin number 2 will just see ground and respond accordingly. We don't have a load right now, so there's no point pushing the button. Also, before we go, we have to power this. So pin number 8 goes to the positive rail right there. Pin number 1 to the negative rail. Pin number 4 is the reset pin. So we looked at that in the last video of this series, and other than the bonus video that I did between, and this is also waiting for basically a negative signal, at least close enough to it, and so we put it directly to the positive rail. That prevents it from doing anything, so that pin's not doing anything now. in an earlier video, we put pin 6 to the negative rail so that it would not do anything. But we don't want to do that in this video. We want it to do something. And so that's pin 6 there. It's going to monitor when the capacitor is charged. For a load, as I said before, we can either have a resistor and LED go to the positive rail or the negative rail. It does matter which direction the LED goes. Doesn't matter order though. So the long lead, the anode, needs to go to the output. Right there I have a jumper going across from pin number 3. And then the short lead, the cathode, goes there. And we might as well move it over here so we can see a little bit better. And I'm going to use a 200 and a 20 ohm resistor, even though there's 1K there. 1K just won't be as bright. If you use higher voltage though, you'll need more than 220 ohms. But for 5 volts, that's plenty fine. And the power is on. And so there we go. Now, quickly, I'm going to pull that. You can see we got false triggering right now. That is why we want this pull up resistor here. And we could have the same problems with removing this jumper at pin 4, the reset pin. It might accidentally reset, and I don't think it's affecting anything now, but there is the possibility. So you want to make sure that you also hold this one high, as well as hold pin number 2 high when you're not pressing the switch. But since we're not doing anything with the reset pin, we don't need to worry about a resistor or anything. We're not going to go to ground. We're just going to hold that high, whereas this one we're going to hold high until we force it low. So now, when it comes to the amount of time, it's based on the RC time constant to get to 2/3 of the power supply voltage. The capacitor is discharged. It's being discharged. Actually, whatever current right now is going through the resistor is going to the negative rail. We'll look at that later. And so the capacitor is not getting charged. Once we hit that button, then the capacitor charges through the resistor right there. So a larger value capacitor will take longer. This is probably the largest value we want to use though with an integrated circuit like this. I'm assuming because it's going to short to ground when you discharge it. And so if you want to go quicker, you could use lower value capacitors or lower value resistors. If we want to do more time, since this is about the largest value I want to use, instead of a 1 kiloohm resistor, I grab the 10 kiloohm resistor. So the capacitor is charging through the resistor right now, and so it's going to take 10 times as long because to 2/3 of the power supply voltage, because it's 10 times the resistance. There's 1/10 of the current over time. When you saw that turn off, the capacitor discharged through pin number 7. And here I kind of drew out what happens within the 555 timer using circuitry. But as I said before, during its stable state, right now the capacitor is not charging, and if it was charged, it discharged directly to ground. It did that internally through the 555 timer. The output is also directly to ground, as long as we keep above 1/3 power supply voltage to the trigger. Actually, as long as we don't drop below. Technically, if we're not giving it a signal, then it won't be below 1/3 of power supply voltage, but there's stray signals in the air and within the integrated circuit and whatnot. But you can see here, this side of the LED is to the negative rail, and the output is also to the negative rail. If we add the green LED, then and put it to the positive rail, so I got the long lead, the anode, up 1, the short lead, the cathode, to the rail, and 1 kiloohm resistor, you can see that one does turn on because it does connect to the negative rail. So we have positive going through the resistor, the LED, to the negative rail. So now, what happens? When we press the switch, we get a low signal because it'll connect directly to ground and get a low signal there. What that's going to do is stop the current from going into pin 7. So basically it's just an open switch. It's not doing anything. The capacitor can charge. And while it's doing that, the output will go high. So it's like connecting to the positive rail. So it's not quite as effective with this particular 555 timer, at least. It's not given exactly 5 volts, but close enough where I'm just going to draw this to kind of indicate that. So you saw when the went back to a low signal, we don't have a resistor to the green LED. There we go. And we'll just remove it. It doesn't really matter. So when it goes back to turning the LED off, it returns to its stable position. The reason why it did was because pin number 6 recognized that the capacitor charged up to 2/3 of the power supply voltage right there. And then, so what that did, that closed the internal switch to the negative rail, discharged the capacitor. At the same time, it set the output low right there. And so the red LED is off, but if we put the green LED or anything else to the positive rail, then it would be on. So you could turn something off for a period of time if you want, but usually you see people turn stuff on. And here's the basic formula. So it's mostly a time constant, RC time constant, but you multiply it by 1.1. So it lasts a little bit longer than the RC time constant of going from 0 to about 1/3 of the power supply. So to make the math easy, 1,000 microfarad is the same as 0.001 farad, because you got to do the math in farads, not microfarad. And then if you multiply that by 1,000 ohms, that's about 1.1 second. After you multiply it by 1.1, you take 1,000 microfarad, 0.0001, which is 1,000ths, times 10 thousandths, you get 10, times 1.1, you get 11 seconds. So pretty straightforward, and a pretty cool circuit right there. You get a timed, so it's a 555 timer. Usually you're using it for timing, even though I like to introduce the flip-flop switch, which responds directly to pushing a button.